Welcome to Let's Turn the Lights on Probability. This is the first of two videos that delve into the Year 9 topics of probability. So I think you'll find them interesting and some interesting applications coming up. So let's get on with it and have a look at this screen. And I want to talk a little bit about the big picture in the middle, because a lot of people think probability is about gambling and your chances of winning, like horse racing. Oh, that's not a good idea. Lose a lot of money there, or poker machines. No, probability is not primarily about gambling. A lot of people use it for that, but there's not much future in gambling. So I want you to think more about some of the applications in the real world that we might come across. So to get you ready for that, come up the top corner here, and we've got a cone. And if you flip the cone over, it may land on its side, or it may, by chance, if you're very lucky, land on its base. So this presentation really is about the experimental probability, where you don't know how to work that out, the chance of a cone landing on its side versus its base. So you have to do an experiment and see if you can estimate the probability by counting up over a number of tosses of the cone, how many land on its side and how many land on the base. So you get that idea. We've seen that in an earlier presentation. The same thing here. This is the result of looking at the number of calls somebody's gotten per day, and what's the most frequent? 2 calls a day occurred 10 times. Frequency meaning the number of times it has happened. So we could estimate now the chances of a person getting 4 or more calls. That would be all that lot there. You'd have to add up how many times they got 4 calls, 5 calls, 6 calls, and there's one there I think was flat, no, nothing there for 7, and 8. So you have to add them all up and work out the experimental probability of getting more than 4 calls. Okay, you couldn't work it out in theory because the chance of getting a call is unknown. It's not like rolling a die and the 6 faces have equal chance. Okay, can't work it out in theory, can we, like that? So come up the top screen here, top of the screen on the right hand side, and here the experiment has been to record the number of apples somebody eats per day. Okay, no apples occurred 10 days, 1 apple 17 days, and so on. So we can make little tables, we can make graphs to record the results of our experiment or our investigation, and then we can work out a experimental probability, which is of course what this a large part of what this video is going to be about. All right, what about this one here? This is what we call a two-way table. There's 2 variables. We're measuring a person's gender, whether they're male or female, and whether they eat breakfast or not. So there's 2 variables there. Okay, so we're going to delve into those in this presentation. Now down the bottom, we've got 2 different ways here of representing the sample space. And here, we haven't seen too much of this before. I've mentioned it before though. This is a tree diagram. You start, this is the first drawer, could be a red or a blue. This column here is a second drawer. It could be followed by another red. Third drawer could be followed by another red. Can you see? This is a great way of finding out the sample space. How many possible outcomes you've got from a 3-drawer from a bag. So there's 3 drawers here, the first one, the second one, and the third one. So it's a good way of working out the sample space. Same thing over here. Only we've got 2 spinners, spinner with numbers 1 to 4 on it, and spinner 2 with numbers 1 to 4. So that's another way of working out all the different items in S. Okay, what does S look like? Let's go back. And so it's a system, isn't it, of looking at that. And we need a system when the problem is a bit more compounded. Compound here. Okay, we keep going back there. So we want to look at a compound experiment where you've got more than just one thing happening. You've got two spinners over here, or over here you've got three draws, not just one draw. So that's called compound probability, or compound event, where you've got more than one thing happening. Let's go down and start to explore some of these things. Okay, so this is a bit of a review of the words that we've been using before in experimental probability, where we're actually going to do the experiment many times and see if we can work out our chances in the long run. That's something we usually use in the long run. What's your chances of getting that? So number of trials, we've seen that before, is the total number of times the experiment is repeated. The outcomes make up the sample space, are the different possible results on one trial of the experiment. Okay, with this experiment, it is a simple one. You have two outcomes, on the side or landing on the base when you flip that cone around. The frequency of a particular outcome, that might be the thing that you're looking for. You might be asking, how many times by chance does the cone land on its base? So that you want to find the frequency of that outcome, because the event you're looking for is that special case of landing on its base. And here's the important thing in our work with experimental probability. The relative frequency is the frequency of that outcome expressed as a fraction. So it's how many did you get out of the total. So it's very, very similar to our basic definition of theoretical probability, where it's the number of times the outcome could occur over the total number of outcomes in the sample space. So that with relative frequency now. It's given a different name because it's not theoretical probability, it's experimental probability. All right, so we're going to use the same sort of language, so I hope you're pretty familiar with that. Look up where you've written it down in your definitions and just make sure. Okay, let's go on now. We're going to do this experiment. We're going to toss this cone around a bit and see how it lands. We're going to do it 300 times. And we're going to record how many times it lands on its side. And we did the experiment, it came to 203. And all the rest were landing on the base. Not a bad outcome there, or number of times landing on the base occurred. That's rather unusual, isn't it? More likely to roll a bit rather than stand up properly. All right, so we're going to use this now. The relative frequency is the number of times the event occurs over the total number of trials. Same idea as chances out of the total in theoretical probability. So we're working with a fraction from 0 to 1, and we're going to define the experimental probability as the relative frequency of the event. So we're doing an experiment, we're measuring the results and working out fractions. The frequency relative to the whole. Here it is, there's its frequency relative to the total number of trials. So what would it be? What's the probability of getting a side? Here it is 203 over 300. Okay, and we usually use decimals for relative frequency. So it comes to approximately, notice that sign, it means approximately 0.677. We've rounded it off, and it's our relative frequency, but it's rounded off, so it's only approximately. It's also an approximate estimate of the experimental probability, because the experimental probability might be a bit reliant upon how many times we do the trials, how many trials we have. Okay, what's the probability of a base then? Well, it's the rest, isn't it? It's 1 minus 0.667, if you like, using the complementary event that we had before. Or you could say it's 97 out of 300, counting them up. So it's approximately, again, approximately 0.323, because we've rounded that off. Okay, so you get the idea. It's the same idea of chances out of the whole, but it's a measure of what actually happened here. It's experimental probability. Okay, let's keep going now and give you a go And here we are. We're going to ask you to find some values of the experimental probability that the coin falls heads and tails and so on. And we've done the experiment here. So normally we'd say probability of a head is a half, probability of a tail is a half. But we're going to try and check it out experimentally. This coin may not be a fair coin. It might be a bit biased. It might not be symmetrically made. So we could actually do some experimental probability on this and see what our value comes to. Does it come to a half? Why might it not come to a half? And so on. Okay, so I want you to pause the presentation and have a go at these 4 problems, and I'll show you the answers in a minute. So have a go. So here are our answers. I hope you were lucky to be able to do some there. Notice the approximate sign where we've tended to round stuff off. These were exact because it was 47 out of 100, which is exactly 0.47. So get used to this approximate sign. It's quite commonly used. Okay, are you going okay? Maybe check with classmates and discuss what's going on there if you're not sure, and with your teacher. Okay, let's go on now. Now, in the last presentation, we started to look at table data, where we found that people tend to make measurements like number of apples somebody's eating per day, and how many days did that happen, the frequency of that. So there's one variable here, and that's the number of apples eaten per day. And what we're going to do now is George has actually kept this table to summarise what he's been doing. And what's the probability on a randomly selected day George will eat exactly 1 apple? Well, from the records he's made of the experimenters eating apples, if you like, he ate 1 apple a day on 17 days out of the total. Well, we better add these up here. Adding this column up, we get 43. So, the total trials of the experiment, that was eating apples, was for total number of trials was 43. So the probability eating 1 apple was the number of times it occurred, 17, over the total number of trials. So we would say it's approximately 0.395 is your probability that he will eat 1 apple a day. At least 3 apples, at least 3. So that's this bunch down here, 3 or more. So there's 4 days. 3 days on which he had 3 apples and 1 day on which he recorded 4 apples. That's 4 out of 43. Remember, it's the frequency over the total number of trials. Just the same idea as creating a fraction as a probability calculation in theoretical probability. Okay, and then we put the approximate sign, don't forget that. Okay, now I would like you to use PR and bracket rather than P. Okay, so that you're distinguishing that from P, meaning permutations. Not that you'd use that in this context, but I like to have PR there. All right, want to have a go? Let's go and do some now. 15B1. We have 4 questions there, and I've done something different here. I've put in very small print down the bottom there the answers. Okay, so try not to look at those. You can't look at them easily. So have a go at the problem and then go and have a look at the answers. So I'll pause the presentation there. You pause the presentation, have a go, check your answers, and don't do them all and get them all wrong. You need to do 1 or 2. Make sure you're getting it right, and so on. I don't know whether you've seen this notation here. See this group notation? It says that when you measured the length of the TV commercial, it went from 20 seconds up to 40, but not including 40 seconds. 40 was in the next group. So that's the less than or equal to. Equal to means it's included. Up to 40 would be less than, but not including 40. 40 would be in the next group. So have a look at that. That might be the first time you've seen that. All right, so have a go and come back now. Okay, probabilities from two-way tables. Okay, two-way tables. Now, this is what we mentioned on the first screen. We're going to measure whether the person is a boy or a girl. So that's measuring that variable, the gender. And we're also going to measure whether they're good at maths. So maths ability is the other variable. Variables are quantities which vary, which we try to make some measurement of. We'll do that in statistics coming up. So what does this mean? Let's look at this business here. 12 girls were not good at mathematics, right? Well, there's the girl column there, and 12 were on this row, so they're not good at maths. 17 boys were good at maths. Okay, so you get the idea of how to read the columns. Excuse me, and the rows. All right, let's go on and look at an example. So there's an example here about males and females eating breakfast or not regularly eating breakfast. Okay, so here, that's a survey was conducted amongst some students at a school. Okay, and there's our results. Now, if you took a randomly selected student, so you don't know their eating habits or whatever, what is the probability that the student is male? Well, let's do some totals. So this is an important adaptation of that original table. So let's add up all the regularly eats breakfast. So that and that come to 140. Does not regularly eat. That and that come to 160. Let's add up all the males coming down this way. There's 155. Females, 145. So whichever way you look at it, we have done a totaling of 300 people. Okay, measuring two variables, the breakfast variable and the gender variable. Okay, so 300 individuals overall have been measured. So, what's the probability of a male? Probability of a male is a number of males out of the total. So, total number of males with this column, 155 out of 300. Do you get it? And approximately 0.517. What about is male and regularly eats breakfast? So you've got to go to the male column. It's got to be male and regularly eats breakfast. So there they are. There's 87 of them out of the 300. Okay, so you converted approximately to the decimal 0.329. All right, what about is female or regularly eats breakfast? Now, or means it could be a female and regularly eats breakfast, so you could do two things. Or it could just be a female who doesn't regularly eat breakfast, or just regularly eats breakfast. So let's have a look. How many are female? So we've got 145. And how many regularly eat breakfast? What have we got? Well, we can't count them twice. So let's look at all the females. So we've got the ones that regularly eat breakfast, 53 and 92. So that's the females who regularly eat breakfast, and the ones who are just female who don't regularly eat breakfast. But then over here you've got the 87 of other people who regularly eat breakfast. So that's the males. So we've got to cover all categories. Now, so we want to link up these three, which satisfy the idea that they are either female or regularly eat breakfast, or both. So this mob up here are female who regularly eat breakfast. So adding all those up, we've got 232 out of 300, approximately 0.773. Okay, so we have to be careful with the wording of the question and what's going on in that table. Let's have a look at D. Is male given that? Oh, now we saw a bit of this before. Given that the student regularly eats breakfast. So in other words, we're told the student is on this line. They have provided a new condition. This is called conditional probability. So what's the probability of the student being a male. Hang on, we've got to go back. Of a student being a male. Let's come back a bit. Okay. What's the probability of a student being a male given that that condition is applied, regularly eats breakfast? So how many? 87 males out of 140. Notice it's out of 140 now, not 300, because the condition was that they regularly ate breakfast. So only 140. You've changed the size of the sample space under this condition. Okay, this was a condition that they had to be regularly eating breakfast. So it came down to a number out of 140, not out of 300. Now, what's the probability of regularly, hang on, let's go back again, regularly eats breakfast given that the student is female? So this time, we're told the condition is it's one of those, that group in there. So there's 145 females. So given that the student is female, means it's out of 145. We know it's in this group here. How many regularly eat breakfast? It's 53 out of 145, or approximately 0.366. Do you get it? This idea of supplying another condition before you work it out. It's not out of the whole total. And the key word here for conditional probability is given that. Okay, so conditional probability is indicated by the idea that before you start, you know something about the group that you're talking about. You're given something. Okay, so think about that. We're going to do some more work with that. And that's going to be important in problem solving in the real world later on. I want you to have a go at some now. So here they are, 15b2, and I put the little box of answers there, but I want you to try the problems first, and don't look at the answers. So I made them fairly small, so I have to peer at them. And see if you can work with this two-way tables, two variables there now that we're measuring in each of these tables. Right, pause the presentation, have a go, and see what you think. Right, let's move on a bit. Here's a practical situation that life insurance companies use. Somebody is tracked over the lifetime of 100,000 people, males and females, 100,000 of each, seeing how long they live. Okay, so let's try and read this. What's this line here say? It says, if we started with 100,000 females we measured, at the age of 15, how many were left? Had any died? Yeah, some have. We still had 99,231 left. You'd expect that. You don't expect people to die much before they're 15. And then, if they were here, if they were one of those, they then went on to live 67 more years. So that would mean they would end up on the average at 82. Okay, 82 years old. So you get what is going on here. And in life insurance, it's possible to insure yourself for something like 30 years, during which time, if you die, your family gets a payout figure. Depends on how much you've paid in, but you can insure your life for $1 million or more. So life insurance policies use this experimental probability here, measured on data collected over many years. Of course, we might have to question that, because would it still be true today for people like it was here? These people, for a long time ago, medical progress has been substantial. So maybe now it's a bit questionable, okay, because this was done many, many years ago, obviously, to track somebody through to ages, look down the bottom here, ages of 95 to 105. Now, what was happening when those people were born is a lot different from what's happening when the people are born today, aren't they? So there's a few restrictions we might have to think about. But life insurance companies do base their charges and whether they'll insure people on experimental observations like this. All right, let's go on now and have a look at an example. So use the life table, so I've put it over here, right next to us, so we can do it. The probability of a male surviving to the age of 20. Okay, well, let's have a look. Age of 20, how many are expected? That many. Out of, over here, the original 100,000. Okay, just remember we start off with that. Okay, so it's approximately, that sign, 0.986. What about the expected age of death of females now 30? Let's go across to the females and down to 30. Here's how many are still alive out of 100,000. We're not asked that though. We're asked how long do we expect them to live if they are now 30. So let's look. This is expected remaining life, 52.2 years. So here we will add that. So 30 plus 52.2 is 82.2. What's the probability of a 35-year-old female living to the age of 70? Let's go to the 35-year-old females there. Here they are. That's how many 35-year-old females there are. They're left from 100,000 when it started the study. Now, living to 70, they're down here. So how many are still alive at 70? 85,120. So this is conditional, isn't it? We come over here, we have that many left out of that many who were 35. So it's approximately 0.865. So get the idea? It's conditional, isn't it? Of the 35-year-old females, so you have to start here, not back at 100,000. So you know they're there. They're alive at 35. How many are still alive at 70? So it's this many out of that many. Get the idea? Tricky stuff, some of this. What's the probability of a 45-year-old man dying before he reaches the age of 80? Let's go to men. 45. How many are there? That. And how many are there at 80 years old? Let's go to 80. And we've got this many are still alive. Now, be careful. This one says dying before that. So it's not the probability of being alive. So we have to take these away. Okay, how many are still alive, will die, sorry, of 49,024. These are the ones still alive. So dying, take them away, would be that figure there, divided by how many we started with, which is this figure here. Because we're given that, it's a 45-year-old man here. So it's conditional. We would not use 100,000 as our group that we start with, because we're told, given that, if you like, the condition 45 years old now. So it's out of 95,138. And just what's the other thing? It's dying. So it's not this figure here. This is how many people are still alive. A little bit of a tricky do there. All right, do you get the idea? Can you see that this probability business is going to be pretty important in life insurance? Let's go on now. And here's your chance, 15C. 7 questions there, and down the bottom I've got the answers again. So pause the presentation and see if you can use the table to work out the answers to those 7. All right, let's go on now. I want to review something that we've done before. It's called the sample space, and it's a set of all possible outcomes, isn't it? And there's a few different ways in which we can actually try and do that. You could list the outcomes. If it's a simple experiment, the sample space is what? Hang on, we'll just get rid of that. Red, blue, green, yellow. That's for a simple experiment. Sometimes the experiment is a bit more of a compound event. There's 2 things happening here, 2 spinners being, no, it's a spinner and a coin. So the grid method allows you to list what the results or the outcomes are for one and the outcomes for the other. So you've got a head and A on the spinner, or a head and B, or a tail and C. So this is more compounding now, compound events, more complicated. And we mentioned this one, the tree diagram. So here, these two methods, these little diagrams or graphs, help us see what the sample space is, and not just listing them out and trying to work it out that way. And this one, of course, is quite complicated because we're drawing three counters, one after the other, from a bag. And we'd have to be told, do we put that back? Do we put the counter back after we draw it or not? And the idea here is the first one could be a red, then another red, and then another red. So that event or outcome would be RRR. Or you could go RRB, a red followed by a red and then a blue. So it's not a bad way of really looking into the total number of outcomes, and that is the sample space, isn't it? Okay, so we're going to have some practice at that now as we get into more complicated or compound probability, compound experiments, compound events, if you like. So here are three questions. I want you to have a go. I've left the answers to these on the next page. So have a go and check your answers. Let's have a look at them. Okay, so there's the answers to those three. Can get quite complicated, can't it, with a number of possibilities or the size of the sample space. So these diagrams help. And I might just note up here, you must have a system. Can you see the system used there? Heads, heads, then put a tail in, then put a tail there, then put the tail in different spots. Okay, might have to check with your teacher on that one. Let's go on now. All right, so back to theoretical probability and things you already know. If a sample space has n outcomes, like 6 sides of a die, n would be 6. And if they're equally likely to occur when you do the experiment once, then each outcome is got a probability of 1 out of the total, isn't it? 1 out of 6 for each side of the die. Okay, if they're equally likely. Simply divide the total probability up into 6 equal parts, or n equal parts. An event, just remembering that word, is an outcome with a particular property or feature. We might want to roll a 3. So rolling a 3, or the outcome of a 3, would be the event we're looking for. And finally, going right back to earlier videos, if you know the outcomes of an experiment are equally likely, the probability of an event is the number of outcomes divided by the total number of possibilities. Number of outcomes corresponding to what you want. So you might want an even number, so that would be 3 evens out of 6 possibilities in the sample space. This is for the die then, okay? But they've got to be all equally likely, okay? Then you can just do a total of so many you're looking for out of a possible total equal to the number in the sample space. All right, let's start using some of those words, because when we use them in math land, everybody knows what we're talking about, rather than have to explain it in detail. All right, let's go on now. Here's an example. A small child has a collection of shapes. Here are the collection of shapes. She chooses one of the shapes at random. Find the probability that is a triangle. Well, you're a budding young mathematician, so at random, is it possible? How would you set this up so she picks one of these at random? Because she might like red colour rather than blue. That's not random, therefore. So she can't look at the colours. But hang on, the shapes are all different sizes as well. It could be actually very hard to set up this experiment the way that diagram is, because some are very small. She may not be able to pick those up as easily. She'll come to the big ones first, maybe. Interesting, isn't it? So think about that. What's the probability of a triangle? Okay, so here, how many triangles are there? 5. Let's go and find them. 1, 2, 3, 4, 5. 5 triangles out of 17 shapes. That's assuming that each one has equal probability of being chosen. And we've already said that randomness might be hard to set up in this situation. Remember what we did before? Put same size tickets in a bag and closed our eyes. The tickets were all the same size, so theoretically they had equal chance of being chosen. We had our eyes closed, so we couldn't read anything or look at the colour. Okay, so that's a bit more random, that one. Now, what's the probability that she chooses one of them to give to her mother, and that is green? How many greenies have we got there? We want circles. Hang on. Circles is conditional probability, isn't it? It's not out of 17 anymore, it's out of circles. So let's just rub this out and find out from the circles. A condition. So there's 1, 2, 3, 4, 5, 6, 7. So down here it's not out of 17 anymore because it's conditional probability. We have changed the conditions of the experiment. It's now not out of just the shapes, it's out of the circles. She collects all the circles first. And how many are green? Well, there are only 2 of them. This one here and this one here. Get the idea? It can be quite fun, and it's important in practice to get your information and to say, is it random or do we know a condition? Is it just everything, or do we know a condition on our experiment that will be out of a subset within the sample space? It's not out of all 17. We're going to isolate the circles first, so it's only out of 7. This will be important later on in your maths experience. Let's go on now. So here are some problems for you. There are 10 problems. So I want you to try and go through with the ideas that we've just done and see how you go. And I'll show you the answers on the next page. So pause it, have a go, do a couple, and toggle forward to make sure you are getting them right before you try all 10 and find they're all wrong because you were doing it incorrectly. All right, away we go. There's your answers for those 10 questions. So I hope you're having some success. Go back and try them again if you're not sure. Okay, let's move on now. All right, so one of the ways in which we could analyse a sample space, because of the complex nature of an experiment, maybe more than one thing happening, like spinners to spinners, is a two-dimensional grid. Okay, so they've each got 1, 2, 3 and 4 on their edges, and they're twirled simultaneously. There's all the possibilities, isn't it? A 1 and a 1, a 1 on one spinner, on spinner 1, a 2 on the other. So I've got them all listed out there. All right, so use your grid to determine probably getting a 3 with each spinner. Let's go 3. Oh, okay, so it's 1 out of 16. There are 16 possible arrangements there. Do we do multiple addition? No, we do multiplication. These 4 go with these 4. 4 lots of 4 is 16, rather than count all these up. A 3 and a 1. Well, we could have a 3 on spinner 2 and a 1 on spinner 1. We could have a 3 on spinner 1, there it is, and a 1 on spinner 2. So there's 2 chances out of 16. Okay, an even result with each spinner. Let's clear all this off a bit. An even result with each spinner is these here. There are 4 of them. A 2 and a 4, 2 and a 2, 4 and a 2, 4 and a 4. Okay, so there are 4 possibilities out of 16. It makes it easier to work out, doesn't it, if you have that grid to help you. All right, let's go on, and here's some more questions for you, 15F, and the answers, excuse me, are coming up. So let's have a look at those now. And 15F. I hope you got a few of those right. And you've got some techniques coming up now, haven't you, that are useful. Let's go on. We've got one more video to go to complete the Year 9 probability. Only one more video to go. So you've done very well, and I'll catch you in that next one. Cheers for now.